For the last 50 years, we've lived by a simple, powerful promise that our computers will just keep getting faster, smaller, and cheaper. It's a promise that has pretty much defined our world. But what happens when that promise starts to break? It's a big question, I know, but it's one we have to ask. Because the silicon chip, that tiny little miracle that powers our entire digital world, is hitting a wall, a hard physical limit. Moore's law was the heartbeat of this revolution. It was this simple observation that the number of transistors we could pack onto a chip would double about every 2 years. That was the engine of exponential growth that gave us everything from smartphones to supercomputers. But that engine is sputtering. And this isn't some far-off, distant problem. As this quote gets at, we are right on the brink. The old trick of just cramming more and more transistors onto a chip is creating some new, really unavoidable problems. And that's forcing us to get, very creative. So, what's the first and most urgent symptom of this limit? It's heat. A whole lot of it. Especially as we push into this new era of massive-scale artificial intelligence. The demand for more power is creating a literal heat wave. So when you hear someone talk about the cloud, this is what you should be picturing. These huge, sprawling data centers, just packed with millions of processors. Every single one of them is like a tiny furnace, and when you put them all together, you get a full-blown inferno. Here's the breaking point. 70 kilowatts. That's how much heat a single high-tech server rack pumps out. It's also the absolute limit for traditional air cooling. We are literally running out of air to cool our most powerful machines. And the stakes here, they're enormous. If just one of these cooling systems fails, the cost is a staggering $10,000 per rack, per minute. It's mind-boggling. And it's not just about the heat, it's about raw power. To keep these data centers running and cool, we are on track to use up to 4% of all the electricity on Earth in just a couple of years. That is just not sustainable. So, okay, if we can't cool our computers down with air, what if we went to the other extreme? What if we made them cryogenically cold? This is what's known as cryogenic computing. The basic idea is you submerge processors and memory in liquid nitrogen, cooling them down to an unbelievable minus 196 degrees Celsius. I know, it sounds like something straight out of science fiction, but the results are very, very real. And the payoff is immediate. Just look at this difference. At these cryogenic temperatures, latency, that's the delay in accessing memory, for standard DRAM drops by a factor of 4. It turns out, in the extreme cold, things just get fundamentally faster. But it's not just about speed, it's also about efficiency. At these temperatures, electrical resistance just plummets, which means way less energy is wasted as heat. As you can see right here, for both types of memory, the energy needed to operate is more than cut in half. Okay, so supercooling is one path forward, but what if, instead of changing the temperature, we change the fundamental building block itself? What if we totally reinvented the transistor? So here's the core idea. Today's transistors work by something called thermal injection. Just imagine having to boil water to get steam to push a piston. It's kind of a brute force approach that wastes a lot of energy as heat. The new idea is tunneling injection. So instead of going over the barrier, it uses a strange quantum effect to let electrons pass right through it without all that wasted energy. Right? The classic transistor is a MOSFET. This new one is a TFET, and that T for tunnel changes everything. It operates on a completely different physical principle, one that isn't held back by the same heat limits that are choking silicon right now. And here's what it looks like. Now, it might seem similar to a standard transistor, but the TFET is designed from the ground up to harness quantum mechanics. It creates this incredibly sharp on-off switch with far less power, and that breaks a fundamental efficiency limit that has constrained chip design for decades. So we've gone from extreme cold to quantum physics. For our third solution, we're going to look for inspiration from the most efficient computer ever created, the human brain. This is called neuromorphic computing. Instead of the rigid step-by-step logic of a CPU, these chips are designed with elements that act like neurons and synapses. A company called BrainChip has actually already brought this idea to market with their Akida chip, which processes information in an entirely new brain-like way. And as BrainChip's CEO says, this isn't just some lab experiment. The whole point is to put this brain-inspired intelligence inside the devices we use every single day. And this is exactly why it's such a breakthrough. The Akida chip runs on milliwatts. We're talking thousands of a watt, which allows for powerful, always-on AI and battery-powered devices. Just imagine a smartwatch that can understand complex scenes, or a drone that navigates itself, or even a voice assistant in your car that's truly private because all the processing happens right there on the chip. So let's recap. Extreme cold, quantum tunneling, and brain-inspired chips. It's pretty clear we're not just waiting around for the next step after silicon. The revolution is already underway and it's happening on a whole bunch of different fronts. And honestly, what we've covered today is just the tip of the iceberg. Researchers are exploring chips made from single-atom-thick graphene, chips that use light instead of electrons, and even theoretical computers that could use DNA for storage. The future of computing isn't a single path forward. It's more like an explosion of incredible new ideas. We're leaving the era of one-size-fits-all silicon and entering a new age of specialized, incredibly efficient, and radically different types of computing. The silicon age completely changed the world, so now we have to ask, what revolutions will this next age bring?